Welcome to The Explainer. I'm absolutely thrilled you're here for what I really consider a true masterclass. Today, we're putting on our cryptographer hats. We're going to dive into something kind of mind-blowing, the complex inner workings of modern block ciphers. We'll specifically be looking at the legendary Data Encryption Standard, or DES. We're going to break down exactly how you hide data so securely that even massive modern supercomputers struggle to crack it.
Here is the syllabus for our masterclass today. We're covering stream versus block ciphers, diffusion and confusion explained, the Feistel network, the avalanche effect, and finally, balancing speed and security. Let's get right into it. Section 1. Stream versus block ciphers. So, before we can go and build the ultimate cipher, we have to lay down the foundational building blocks of modern cryptography. And that really starts with choosing our architecture. There are basically two main ways to encrypt digital data: stream ciphers and block ciphers. Now, a stream cipher encrypts a digital data stream bit by bit or byte by byte. But here's the catch. It requires a key stream that's securely shared between users in advance over an entirely independent channel. Think about the internet today. If you're dealing with massive data traffic, that introduces a completely insurmountable logistical problem, right? And that brings us to the block cipher. Instead of going bit by bit, it takes a whole block of plain text, usually 64 or 128 bits at a time, and treats it as a single unit to produce a cipher text block of the exact same length. Because they're just so incredibly versatile, block ciphers absolutely dominate the vast majority of modern network-based cryptographic applications. Let's think about the flow of these two architectures. With the stream cipher, you have a setup relying on a bit stream generation algorithm, pumping out a continuous key stream that combines with a plain text bit by bit. But with the block cipher, you've got entire bit-bit blocks of plain text going right into the encryption algorithm as one single unit alongside the key, and popping out the other side as a complete block of ciphertext. It's this block approach that we're going to laser focus on today.
Section 2. Diffusion and confusion explained. So how do we actually make these blocks secure? Well, to give our masterclass some real historical authority, we've got to look back to 1949 and a brilliant guy named Claude Shannon. He introduced this idea of a product cipher, which is essentially just executing two or more simple ciphers in sequence. Shannon proposed that the ultimate cryptographic system needs to alternate between two totally fundamental building blocks: confusion and diffusion. Let's break down what those actually mean.
First up is diffusion. You see, if an attacker knows the frequency of certain letters or words in your language, say how often the letter E appears in English, they can use that statistical structure to reverse engineer your key. Diffusion is what completely destroys that advantage. It takes the statistical structure of the plain text and dissipates it right into the long-range statistics of the ciphertext. Basically, in simple terms, diffusion makes absolutely sure that just one single piece of plain text affects many, many pieces of the final ciphertext.
Now, while diffusion hides the plain text, confusion is your ultimate key hiding mechanism. The goal of confusion is to make the relationship between the statistics of the ciphertext and the actual value of the encryption key as complex as humanly possible. Even if a really smart attacker gets a handle on the ciphertext, the mathematical process under the hood is so hopelessly tangled that the key simply cannot be deduced. It's a brilliantly frustrating puzzle for anyone trying to crack it. To really picture how diffusion works in the real world, think of it kind of like an averaging operation. Imagine taking a message made of characters, and your encryption step involves averaging several successive letters together to get your new ciphertext letter. Because you're averaging them, if you change just one single input character, you automatically alter multiple outputs in the final ciphertext. The original statistical patterns of your message get completely smeared and spread out across the board.
Section 3. The Feistel network.
Okay, now that we have our theory down, let's step into the engine room. How do we actually build a system that achieves this perfect blend of diffusion and confusion? The answer is the Feistel structure. Proposed by Horst Feistel, this is the exact architecture used by a massive number of symmetric block ciphers today, including DES. Here is the step-by-step path your data takes through just a single round of a Feistel network. First, you take your plain text block and chop it evenly into left and right halves. Second, you take a specialized round function, we'll just call it function f, and apply it to the right half along with a subkey. Third, you take the result of that function and XOR it with the left half. And finally, you swap the left and right halves. Let's trace that step by step right now. You can envision the input splitting into an initial left and right half. You see the right half dropping straight down into that F box where it meets the first subkey. Then the result crosses over, hits our XOR operation, combines with the left half, and then, boom, they swap places for the next round. And the data just keeps traveling down, repeating this exact same dance over and over again. Now you might be wondering, why 16 rounds? Why not just do it once? Well, the whole essence of the Feistel cipher is that a single round offers pretty inadequate security on its own. But by repeating it, taking the output of one round and feeding it directly into the next, again and again, you weave this unbreakable web of diffusion and confusion.
So the crucial question is, how do we actually decrypt this massive knot of data? Honestly, this is the sheer brilliance of the Feistel network. You don't actually need to write a whole new algorithm for decryption. Think of the encryption process like a train moving down a track through 16 different stations. To reverse the cipher, you just put the train on the exact same track and send it backward. You feed the ciphertext in, use the exact same algorithm, but simply apply the subkeys in reverse order, starting with the 16th key and ending all the way back at the first.
And the math proves it out perfectly. When you compare a late encryption round with an early decryption round, you notice how the mathematical operations just perfectly mirror each other. The exact same F function, using the exact same subkey, perfectly undoes the XOR operation from the encryption phase. The algorithm flawlessly works in reverse. It's so elegant.
Section 4. The avalanche effect.
We've built the Feistel network, so now let's put it through a theoretical stress test. I want you to imagine a microscopic change. You type out a message, but you decide to change just one single microscopic bit of the starting plaintext, literally just a 0 becoming a 1. What happens to the final encrypted output? Does it look mostly the same?
Well, if the output looked mostly the same, an attacker could easily use those tiny variations to make educated guesses. To prevent this, our cipher absolutely must have what's called the avalanche effect. This is a highly desirable property, where a tiny change in either the plaintext or the key produces a massive, significant change in the ciphertext. Think of it like a tiny pebble starting a massive avalanche on a snowy mountain. Let's walk through a totally concrete scenario to see this in action. Let's look at a starting point where plaintext 1 starts with a 0 and plaintext 2 starts with a 1. That is a single 1-bit difference in an entire 64-bit block. Now watch what happens as it cascades through the Feistel rounds. By round 3, that single changed bit has infected the block, and now 18 bits differ between the two messages. By the time we hit round 16, you get completely different hexadecimal outputs.
The punchline here is the number 32. Exactly 32 bits change entirely after 16 rounds. A single 1-bit difference in the input resulted in exactly half of the 64-bit output flipping completely. The avalanche is absolute. The attacker is left with absolutely nothing to latch onto.
Section 5. Balancing speed and security.
For our final lesson, let's conclude the masterclass by bringing this perfect theory back down to real-world performance implications. Because, let's face it, in computer science, everything is a trade-off. When designing or choosing a block cipher, tweaking the parameters directly boosts your defensive armor. A larger key size means greater security. It ramps up the confusion and makes brute force attacks practically impossible. And increasing the round number? That means more cycles of the F function, drastically increasing the difficulty for any crypto analyst trying to untangle the math.
But then we have the block size. A larger block size, like stepping up from 64 bits to 128 bits, means greater diffusion and overall security. The data is smeared over a much wider area. But here's the rub. Higher security almost always comes at the cost of processing speed. A smaller block size means faster algorithm execution. When your encryption is embedded in high-traffic applications, execution speed is a major concern. You are constantly balancing the armor of your cipher against the speed of your network.
Which brings us to our final thought. The original DES used a 56-bit key. Today, off-the-shelf multi-core processors and supercomputers are capable of over 1 billion key combinations per second. They can brute force a 56-bit key in a matter of hours. This is exactly why understanding these foundational concepts, diffusion, confusion, the avalanche effect, is absolutely vital as we transition to newer algorithms like AES with 128-bit or even 256-bit keys. The math is brilliant for sure, but the compute power of the world is always catching up. Thank you so much for joining me for this explainer. I really hope this masterclass gave you a clear picture of how block ciphers actually work, and maybe leaves you wondering, just how secure is the data you sent today?